In the quiet years of the late 17th century, long before the modern world learned to pierce the darkness with electric light, a single explanation emerged that seemed to bind the heavens and the earth with one sweeping idea. Isaac Newton, working through long nights filled with calculation and reflection, uncovered a relationship so simple in form, yet so powerful in reach, that it reshaped human understanding of motion itself. When he published his Principia in the year 1687, the scientific world saw not just a new theory, but a new way to read the universe. Every falling apple, every drifting comet, every turning moon suddenly obeyed the same universal rule. Newton's law of universal gravitation declared that all masses attract one another. The strength of this attraction depended on the product of the masses and diminished with the square of the distance between them. It meant that the Earth pulled on the Moon and the Moon pulled on the Earth. It meant that the Sun held the planets in their orbits, not through invisible strings or perfect geometric harmony, but through a force that extended across space itself. This invisible influence operated instantly, with no delay, creating an elegant structure where motion could be predicted and traced with clear mathematical precision. For astronomers who had struggled for centuries to understand the wandering patterns of planets, this idea was transformative. The elliptical paths that Johannes Kepler had described with geometric rules now had a physical explanation. Newton's formulation allowed scientists to compute the exact motion of Earth around the Sun, the speed of the Moon as it circled Earth, and the sweeping arcs carved by comets that returned after long journeys through the darkness. Planets no longer drifted under mysterious influences. They moved according to a single law linking all bodies under one cosmic thread. The success of Newton's law inspired confidence that spread far beyond theory. It guided practical attempts to measure the Earth's shape and size. Through geodetic surveys, scientists learned that Earth was not a perfect sphere, but slightly flattened at the poles and widened around the equator. This matched Newton's prediction that a rotating planet would bulge outward due to its spin. Lunar distance measurements allowed researchers to refine the understanding of gravitational influence across the space between Earth and its nearest celestial companion. With each new measurement, Newton's framework proved itself again. Even more striking was the discovery of Neptune. When Uranus drifted slightly from its predicted orbit, two mathematicians set out to find the cause using only Newton's equations. They concluded that an unseen planet must be tugging at Uranus, shifting its path by a barely perceptible amount. In 1846, telescopes pointed toward the predicted location and revealed Neptune almost exactly where the calculations insisted. It must be. This moment felt like the purest demonstration of the power of Newton's law, a triumph where mathematics revealed an unseen world with nothing but logic and gravity. Yet beneath this triumph, a quiet discomfort began to form. Newton had described how gravity acted, but not what it was. He could not explain how one mass influenced another across empty space with no physical connection. This action at a distance, instantaneous and unmediated, worked perfectly in the equations, but lacked a mechanism. For a time, the absence of explanation felt acceptable because the predictions were so accurate. But as physics advanced, especially with the rise of electromagnetic theory, the idea began to feel incomplete. By the mid-19th century, scientists knew that changes in electric and magnetic fields propagated at the speed of light. Nothing appeared capable of traveling faster. This posed a subtle but unavoidable contradiction. If gravity acted instantaneously across any distance, then it demanded a speed beyond the universal limit shown by Maxwell's equations. Gravity could not remain both instantaneous and compatible with the growing understanding of light and electromagnetism. The universe seemed to be offering a clue that the foundations of physics needed more than refinement. They needed reimagining. The tension did not end there. Mercury, the swift innermost planet, revealed another puzzle. Astronomers documented its orbit with exceptional care and noticed that its closest point to the Sun drifted over time. Most of this motion could be explained by gravitational influences, but a small remainder, 43 arcseconds per century, refused to disappear. Attempts to blame measurement errors failed. The idea of an unseen planet named Vulcan was proposed and searched for repeatedly, yet nothing was found. The inconsistency persisted, quiet but stubborn, like a faint signal waiting for someone to hear it. The more carefully observers measured the motions of planets, the more these cracks in Newton's perfect geometry became undeniable. They did not overthrow the law. They did not undermine its immense practical value, but they suggested that the universe held deeper structures beneath the surface, waiting for a new way of understanding motion, time, and space itself. The 19th century approached its end with gravity standing both triumphant and incomplete. Newton had drawn the grand outline of the cosmic picture. Now the task was to reveal what lay beneath the outline, hidden in the fabric of reality. The 19th century unfolded with growing precision in observation and increasing confidence in measurement, and with each improvement, the faint inconsistencies in Newton's gravitational picture became harder to ignore. Telescopes sharpened their view of the planets. Timekeeping improved. Observatories spread across continents, comparing results and reducing uncertainty. What once might have been dismissed as observational, error now appeared as a persistent signal. The universe was whispering that Newton's elegant rule, though powerful, was not complete. Mercury's stubborn deviation was the most famous clue, but it was not the only one. Each attempt to refine planetary motion revealed that Newton's view of gravity, while overwhelmingly accurate, did not perfectly match the sky. Astronomers tightened their calculations, considered the influence of every known planet, and accounted for the complex gravitational interactions in the solar system. Yet the unexplained drift in Mercury remained. It was too precise, too steady, and too thoroughly confirmed to be illusion. Nature rarely provides such consistency without purpose. Something fundamental was missing. Even more unsettling was the growing conflict between Newtonian gravity and Maxwell's electromagnetic theory. While Newton's framework required gravity to act instantly, Maxwell had revealed that disturbances in electric and magnetic fields traveled at the speed of light. If light represented the maximum speed of causal influence, then gravity could not outrun it without violating the very structure of physical law. Scientists did not yet know how to resolve this contradiction, but they felt its weight. Physics was being pulled between two towering achievements that could not coexist comfortably. To some, the solution seemed obvious. Perhaps there truly was an unseen object near the Sun. The imagined planet Vulcan became a serious candidate for many years. Astronomers planned their searches during solar eclipses, when the blinding glare of the Sun briefly yielded to a darkened sky. They scanned for a small moving dot whose presence could restore harmony to Newton's equations. A few reported possible glimpses, but none could be repeated. None held up under scrutiny. Each failed search weakened the hope that the anomaly was simply missing matter. As the search for Vulcan faded, new conversations emerged among physicists wrestling with deeper questions. What exactly was gravity? How did masses know to pull on each other? What filled the space between celestial bodies that allowed a force to appear across emptiness? Newton had offered no mechanism, admitting candidly that he did not attempt to explain the cause of gravity. He described the effect only. But in a world increasingly shaped by the study of fields and waves, an explanation limited to mathematical description no longer felt satisfying. Scientists wanted a theory that did not merely describe the universe, but revealed what lay beneath the surface of its motions. At the same time, a conceptual shift was quietly taking shape in the scientific imagination. If light speed was absolute, then time itself could not be rigid. If fields carried energy and momentum across space, then space could not be the static, untouched backdrop Newton had assumed. These ideas had not yet formed a coherent theory, but they hinted that solving gravity's remaining mysteries might require rethinking the very stage on which all physical events played out. Despite these growing concerns, Newton's law remained deeply trusted. Engineers building structures relied on it. Navigators charting the heavens trusted it. Astronomers predicting planetary motion depended on it. The law worked so well in nearly every context that its shortcomings felt more like clues than failures. Scientists faced a delicate balance. They could not discard a law that had guided physics for centuries. Yet they could not ignore evidence showing that the universe behaved in ways the law did not fully capture. By the end of the 19th century, physics found itself suspended between mastery and mystery. The great successes of Newton's gravity remained solid, yet the cracks in its foundation glimmered in the light of new discoveries. Mercury continued its quiet rebellion. Electromagnetic theory insisted on a universal speed limit. The concept of instantaneous action became harder to defend, and the universe, in its silent precision, was waiting for someone who could see the next layer of truth hidden beneath the old. As the 19th century drew toward its final years, the scientific world stood within a strange tension. On the surface, the Newtonian universe still appeared calm and orderly. Predictions worked. Equations matched almost everything observed. The planets continued their ancient journeys with reliability that seemed to confirm Newton's brilliance every night. Yet under this calmness, the inconsistencies would not fade. They lingered like faint ripples on still water, hinting at something stirring deep beneath. Mercury's orbit remained the most persistent signal. Generation after generation of astronomers returned to the same question and found the same result. The perihelion of Mercury shifted slightly more than Newton's law allowed. Each advance in instrumentation confirmed its value with growing certainty. 43 arcseconds per century was not a guess. It was a measurement that refused to bend. Scientists tried every reasonable explanation before entertaining the unthinkable. They adjusted planetary masses, re-evaluated the pull of Venus and Earth, revisited the known irregularities of the Sun, and refined their calculations with extraordinary care. Yet every path that followed Newton's logic ultimately reached the same impasse. The more precise the observations became, the clearer the conflict stood. A theory that explained so many grand phenomena might still overlook something hidden. Did gravity change slightly near the Sun? Did the structure of space behave differently under intense conditions? These questions were not yet asked openly, but they formed quietly in the minds of those who studied orbital motion. The universe was revealing a boundary, a place where Newton's description began to strain beneath the weight of reality. Meanwhile, a deeper issue emerged at the intersection of gravity and light. Maxwell's electromagnetic equations had reshaped the world's understanding of energy and radiation. These equations showed that light traveled at a fixed speed, a speed that seemed to limit how fast influence could move from one place to another. Yet Newton's gravity ignored this limit entirely, acting without delay across even the greatest distances. If a star lost mass or shifted suddenly, Newtonian physics implied that every object in the universe would feel the change instantly. But if light could not outrun its own speed, how could gravity? Scientists sensed a contradiction forming between two of the most successful theories ever created. Both could not be entirely right in their current form. The search for Vulcan became a final effort to protect Newton's perfect universe. If a small planet existed close to the Sun, its gravitational pull might account for Mercury's strange behavior. Astronomers scanned the sky during eclipses when the bright solar glare diminished. They searched with patience and optimism. Some thought they glimpsed something. Others doubted the reports. In the end, no reliable evidence of Vulcan appeared. The more determined the search, the more obvious it became that the solution could not be found by adding new pieces to the solar system. Something deeper was shifting. At the same time, the growing fascination with fields and waves suggested the universe might not be built on forces acting across emptiness, but on interactions shaped by the medium of space itself. Scientists began questioning whether empty space was truly empty. If electric and magnetic fields could travel through it with structure and speed, perhaps gravity possessed a similar nature. Yet no one had found a way to reconcile this idea with Newton's instantaneous attraction. The problem sat unsolved, like a locked door waiting for a new key. Despite all this, Newtonian gravity remained essential in daily scientific practice. Engineers used it to design roads and bridges. Navigators used it to guide ships across oceans. Astronomers used it to track comets and plan observations. The law proved itself in countless applications, reminding everyone how deeply it was woven into the fabric of understanding. The cracks that appeared did not erase its power. They instead revealed that the Newtonian world, while incredibly successful, was not the whole story. It was a masterpiece missing one final layer. As the century closed, physics stood poised on the edge of transformation. The skies had delivered a subtle message. The equations of gravity, beautiful as they were, did not reach far enough. Something new was required, something capable of explaining Mercury's orbit, honoring the speed of light, and giving gravity a mechanism as real as the electromagnetic fields already known. A greater truth hovered just beyond human reach, waiting for a mind willing to look at the universe from a completely different angle. Long before his name became a symbol of genius, Albert Einstein moved through the world with a quiet intensity that often went unnoticed. The popular image of him as a prodigy overlooks the truth. His early academic life was far from effortless. He struggled to secure stable employment. Professors did not immediately recognize him as extraordinary. After completing his studies, he found himself unable to obtain a university position, eventually taking work as a technical expert at the Swiss Patent Office in Bern. Yet it was in that modest setting, surrounded by stacks of engineering diagrams and applications, that his most transformative ideas began to take shape. The world saw an office clerk. He saw a universe filled with unanswered questions. Einstein carried with him a deep curiosity about nature's most basic principles. Even in his youth, he wondered what it would feel like to chase a beam of light. That simple question, so childlike in its imagination, quietly pushed him toward a revolution. If one could somehow travel alongside a beam of light, would its waves appear frozen? Maxwell's equations insisted that light always moved at a constant speed, regardless of the observer. The idea that light could appear still violated everything physics then believed about motion. This contradiction gnawed at Einstein year after year, even as he worked through piles of patent applications that described electrical devices, machinery, and technical mechanisms. Each application, in its own way, helped sharpen his sense for how physical laws applied to real machines and real measurements. The scientific community of the late 19th century assumed the existence of something called the ether, a hypothetical medium through which light waves were thought to travel. Just as sound waves needed air and ripples on water needed a surface, light was imagined to require an invisible substance filling all space. To detect this ether, physicists built elaborate devices. The most famous was the Michelson-Morley interferometer, designed to measure the Earth's motion through the ether by comparing the speed of light in different directions. If Earth moved through this medium, the speed of light should vary slightly. But the result was astonishing. There was no detectable change. Light behaved as though no ether existed at all. This null result was more than a failed detection. It was a direct challenge to the very foundation on which 19th century physics rested. If light's speed remained constant no matter how the Earth moved, then something about the nature of motion itself needed to be reconsidered. Most physicists of the time tried to protect the ether by adding complicated explanations. They imagined that the Earth dragged the ether along, or that the apparatus contracted just enough to hide the expected effect. Einstein, however, approached the problem differently. He accepted the result at face value and asked what the universe must be like if the speed of light truly remained unchanged for all observers. The answer required rethinking time itself. If the speed of light never varied, then clocks in relative motion could not measure time in the same way. Events that seemed simultaneous to one observer would not be simultaneous to another. Time would stretch or compress depending on how one moved. Lengths would shrink along the direction of motion. These ideas sounded impossible, yet they followed directly from the assumption that the speed of light was constant for everyone. Einstein did not invent these conclusions. He revealed that they were woven into the fabric of reality, waiting for someone to see them clearly. Even as Einstein developed these thoughts, he recognized a deep incompatibility between Newton's gravity and the principles forming within his mind. If no information could travel faster than light, then Newton's instantaneous action at a distance could not be correct. Gravity, according to Newton, communicated its influence across any distance with no delay. Yet Einstein's growing view of time and motion demanded a universal speed limit. The two frameworks could not coexist. Something in Newton's description had to give way. Still, Einstein did not yet possess the mathematics to propose a new theory of gravity. His early papers hinted at a connection between acceleration and the effects of gravity. He suggested that someone inside a closed room could not distinguish between being pulled downward by gravity and being pushed upward by acceleration. This simple idea would eventually become a cornerstone of his later work, but at this stage, it remained a quiet insight, something that would gain meaning only years later. For now, Einstein focused on building the structure that would become special relativity. He showed that the equations describing motion must change if the speed of light was constant. He showed that energy and mass could no longer be treated as separate. He showed that space and time formed a united geometry rather than existing as independent quantities. These discoveries were not the results of speculation. They were logical consequences of experimental facts. Michelson and Morley had provided the crucial clue. Maxwell had laid the mathematical groundwork. Einstein brought the pieces together. Yet as profound as special relativity was, it did not solve the mystery of gravity. It exposed the flaw in Newton's formulation. It revealed that instantaneous action violated the fundamental behavior of light. But it did not explain how gravity actually worked. The path forward required an even deeper shift, one that would take Einstein beyond the physics of motion and into the geometry of space itself. Einstein's life inside the patent office continued with its quiet rhythm, but inside his mind, the boundaries of physics were beginning to bend. He spent long evenings walking through the streets of Bern, replaying the implications of a universe where time and space refused to behave as they once had. He felt the weight of the Michelson-Morley result and the elegance of Maxwell's equations pressing together, demanding a new way to understand motion. While others tried to rescue the ether with increasingly complex assumptions, Einstein stripped the problem to its essentials. What if the ether simply did not exist? What if light needed no medium at all? This perspective allowed him to examine the world without carrying the assumptions that had trapped earlier thinkers. If the speed of light remained constant for every observer, then the structure of time itself could stretch and contract depending on motion. Einstein realized that the universe was not accommodating human intuition. Instead, intuition had to adapt to the universe. Time dilation and length contraction were not tricks or illusions. They were measurable consequences of motion. A fast-moving clock would genuinely run slower. A rapidly moving object would genuinely shrink along its direction of travel. These were not philosophical curiosities, but physical facts embedded in the equations. As Einstein developed these ideas, he understood that they pointed to something deeper than a revision of mechanics. Newton had assumed that time flowed identically everywhere, a universal rhythm that never changed. He had assumed that space extended infinitely in straight lines, unchanging and unmoved. But if time depended on motion and space changed with speed, then Newton's foundations needed to be rebuilt. This shift did not come from speculation. but from carefully reconciling the constancy of light with the rules of motion. The universe had spoken through experiment. Einstein listened more closely than anyone else. Inside the patent office, he refined his thoughts quietly. Many of his early calculations were done during lunch breaks or late in the evening. The atmosphere of the office, far from the academic world, gave him the freedom to think without pressure or hierarchy. He studied electrical systems, mechanical devices, and measurement tools that filled the patent submissions. Each one, in a small way, sharpened his appreciation for the precision required to understand physical laws. Devices that relied on timing or synchronization reminded him that even a tiny misalignment could distort an entire system. These experiences reinforced his conviction that time was not absolute, but depended on motion and measurement. By the year 1905, Einstein had built the framework that would become special relativity. The theory described how space and time formed a unified structure, now known as spacetime. This structure responded to motion with predictable and testable consequences. Yet, at its heart, special relativity emphasized a limit that no object or signal could exceed. Light was the ultimate messenger of physical information, and nothing could move faster. This principle stood in complete opposition to Newton's instantaneous gravity. If gravity transmitted its influence instantly, it would violate the very limit that special relativity placed at the center of physical law. Einstein realized that the conflict was not optional. To move forward, physics needed a new description of gravity, one that honored the speed of light and treated time and space as flexible, not rigid. This realization did not immediately produce a solution. It marked the beginning of a long struggle that would take Einstein a decade to navigate. The tools he had at the time were not enough. Still, he sensed a path forward through a simple question he had once imagined with almost playful curiosity. If someone inside a closed room felt weight pressing down, could they tell whether that force came from gravity or from the room accelerating upward? Einstein recognized that no measurement inside such a room could distinguish between these two experiences. Gravity and acceleration felt identical. This insight, simple and accessible, carried immense implications. It hinted that gravity might not be a force acting across space, but a manifestation of motion itself. The seed of this idea would eventually bloom into the equivalence principle, a concept that would guide Einstein toward a new theory of gravity. But during these early years, the idea remained a quiet spark rather than a finished truth. Einstein continued to explore the consequences of special relativity while knowing that gravity, the most ancient of forces, still waited for its transformation. As he refined the mathematics, he sensed that the universe was not built upon separate laws for motion, light, and gravity. Instead, these domains were woven together, waiting for a single framework to unite them. Special relativity had corrected our understanding of time. The next challenge would be to correct our understanding of gravity itself. Einstein stepped into the new century carrying ideas that had already begun to unsettle the foundations of physics. Special relativity had revealed a universe where time flowed differently for observers in motion and where distances contracted depending on speed. These concepts were not mathematical curiosities, but measurable truths about the structure of reality. Yet Einstein knew that his work was incomplete. A universe built on the constancy of light still lacked a gravitational law that could live within those boundaries. Newton's gravity acted instantly. Special relativity insisted that nothing could outrun light. These two pillars could not support the same universe. One of them had to change. Einstein sensed the next step through a thought experiment so simple that anyone could imagine it, yet so profound that it would become the key to reshaping physics. He pictured a person in a sealed chamber, floating freely in space. If the chamber suddenly accelerated upward, the person inside would feel pressed to the floor, just as though gravity were pulling downward. Conversely, if the chamber drifted smoothly through space with no acceleration, the person would feel weightless, just as though they were falling freely in a gravitational field. This realization struck Einstein with the force of inevitability. Gravity and acceleration were not merely related. In a small region of space, they were indistinguishable. This insight became the equivalence principle, though Einstein had not yet named it. It was the bridge between his understanding of motion and his curiosity about gravity. If acceleration could mimic gravity perfectly, then perhaps gravity was not a force in the Newtonian sense. Perhaps it was a feature of motion itself, something that shaped how objects followed their natural paths. Every time Einstein returned to this idea, it opened new doors. It suggested that the effects attributed to gravity might arise from the geometry of space-time, rather than from an instantaneous pull between distant masses. But even as this vision began to take shape, Einstein faced a daunting challenge. He needed mathematical tools far more powerful than those he had used to build special relativity. Newton's gravity relied on simple relationships. Special relativity introduced the geometry of space-time, but kept it flat and uncurved. To describe gravity in a universe where acceleration and gravity mirrored each other, Einstein needed a language that could describe curved surfaces, warped distances, and non-uniform paths. Such mathematics existed, but lived in a corner of the mathematical world rarely visited by physicists. Riemannian geometry, developed decades earlier by Bernhard Riemann, allowed space to bend and twist in ways that ordinary Euclidean space could not. Einstein knew that this was the direction he needed to explore, yet he struggled with the mathematics. His background had given him the intuition to imagine how the universe might behave, but not the tools to express those ideas formally. This difficulty slowed his progress and tested his patience. He would spend years oscillating between physical insight and mathematical frustration. Each time he thought he understood the geometry, the equations slipped away from him, revealing new complexities. Yet he persisted, guided by the conviction that the universe could not be contradictory. If light had a fixed speed, and if acceleration could imitate gravity, then gravity must emerge from the behavior of space-time itself. While Einstein wrestled with these ideas, the scientific world remained unaware of the transformation taking place in his mind. He continued working at the patent office, reviewing designs and proposals that arrived day after day. His colleagues respected him, but did not recognize that he was building the foundations of a new physics. The quiet, steady rhythm of his work environment gave him the space to think, and the contrast between his ordinary job and his extraordinary insights only sharpened his focus. He learned to trust the clarity of simple thought experiments. He avoided speculation and relied on reasoning grounded in measurable reality. By this time, The incompatibility between Newtonian gravity and special relativity had become undeniable. If gravity were instantaneous, it would violate the very principles that define the structure of space-time. But if gravity traveled at a finite speed, then Newton's equation needed to be replaced, not merely adjusted. Einstein understood that a successful theory of gravity would have to do more than match observations. It would need to integrate seamlessly with special relativity, reveal why Newton's law worked so well in most situations, and explain the small but persistent anomalies that Newton could not address. The path forward was not obvious, but Einstein felt its outline becoming clearer. Gravity had to be woven into the geometry of space-time. Objects should move along the natural curves of that geometry, not because they were pulled by a force, but because the structure of space-time itself guided their motion. This realization marked the beginning of a journey that would carry Einstein toward one of the greatest achievements in the history of science. It was the moment when gravity began to shift from a mysterious force to a geometric feature of the universe. The transformation was coming. The century that had begun with quiet tension would soon witness a revolution that reshaped our understanding of the cosmos. Einstein stood at the threshold, prepared to step into a new vision of gravity that would explain not only the motions of planets, but the true nature of space and time. Einstein entered the year 1907 with a mind still orbiting the questions that had haunted him since his earliest fascination with light. He had already reshaped the understanding of motion through special relativity, yet the mystery of gravity loomed ahead like a distant peak obscured by clouds. He knew that Newton's instantaneous attraction could not survive in a universe where no signal traveled faster than light. But he did not yet know how to replace it. His breakthrough arrived unexpectedly during an ordinary moment when an extraordinary idea fell into place with breathtaking clarity. He later described it as the happiest thought of his life. He imagined a person falling freely from the roof of a house. During the fall, the person would feel weightless, as if gravity had vanished entirely. Objects would float beside them. Every experiment performed in that falling room would suggest that gravity was gone, even though the person was deep within the Earth's gravitational field. From this simple picture, Einstein recognized something profound. Gravity could be made to disappear locally by moving in a particular way. In that small region of spacetime, the effects of gravity and the effects of acceleration were indistinguishable. This idea was more than a curiosity. It was the key that opened a new vision of the universe. Einstein realized that if gravity could be cancelled by choosing the right motion, then gravity might not be a traditional force at all. It might be a manifestation of the geometry of space-time, shaping the paths of objects not by pulling them, but by guiding them along natural curves. The equivalence between gravity and acceleration became his compass, pointing toward a deeper structure that waited to be uncovered. Yet turning this insight into a theory required a mathematical language capable of describing curved spaces. The familiar coordinates used in ordinary geometry were not enough. Einstein needed a way to express how distances changed depending on position, how directions shifted, and how lines that appeared straight in one system could bend in another. Fortunately, such a framework already existed in the world of pure mathematics. Bernhard Riemann had developed ideas about curved surfaces decades earlier. ideas that described how geometry could change from point to point. But these ideas were intricate and unfamiliar to most physicists. Einstein was not trained in this area, and the complexity of Riemann's geometry stood like a wall between intuition and formal theory. Understanding it required patience, persistence, and a willingness to learn methods far removed from the mathematics used in engineering or classical mechanics. It was during this phase that Einstein turned to his old friend and former classmate, Marcel Grossmann. Grossmann, a mathematician with deep understanding of the tools Einstein needed, recognized immediately that Riemann's geometry contained exactly the structures required to describe a curved spacetime. Together they began to translate Einstein's physical ideas into the language of tensors, metrics, and curvature. The metric tensor provided a way to calculate distances and times in a curved spacetime. The curvature described how space-time bent in the presence of mass and energy. Einstein realized that objects in free fall were not being pulled by a force. They were simply following the straightest possible paths in a curved geometry. What Newton had called a force was actually a reflection of space-time's shape. This new picture was not a rejection of Newton's work. Instead, it revealed why his law worked so well. In regions where gravitational fields were weak and velocities were small compared to the speed of light, spacetime remained nearly flat. In such conditions, Einstein's new equations reduced naturally to Newton's familiar inverse square law. Gravity, as Newton described it, emerged as an approximation of a deeper truth, just as a flat map approximates the curved surface of Earth. Einstein and Grossmann spent years refining the mathematics. Progress was slow and often frustrating. Equations that looked promising at first sometimes collapsed under scrutiny. Attempts to match known physical results forced them to return repeatedly to the drawing board. But each failure sharpened their understanding. Each setback brought them closer to the correct form. Slowly, the universe began to reveal its structure. By 1915, after nearly a decade of effort, Einstein uncovered the equations that described how matter and energy curved space-time, and how that curvature guided the motion of everything within it. These field equations were compact yet deep, elegant yet immense in implication. They transformed gravity from an invisible pull into the dynamic geometry of space-time. The publication of these equations marked the birth of General Relativity. It was a moment when physics expanded beyond the boundaries that had defined it for centuries. The new theory did more than repair the inconsistencies of Newtonian gravity. It predicted phenomena that no previous theory had imagined. Light would bend as it passed near a massive body. Time would slow in strong gravitational fields. Planetary orbits would deviate by exactly the amount Mercury had been whispering for generations. These were not speculative visions. They were measurable consequences of curved space-time waiting to be tested. The universe had offered hints. Einstein had followed them to their source. A new understanding of gravity had arrived, reshaping the way human beings perceived motion, energy, and the fabric of reality itself. Einstein stood at the threshold of a new universe, yet the path before him was far from smooth. The idea that gravity was not a force but a reflection of curved space-time was bold, elegant, and deeply intuitive to him. But intuition alone could not unveil a physical law. The real world demanded equations that worked. equations that predicted measurable outcomes, equations that held together under every mathematical test. Between 1911 and 1915, Einstein moved through one of the most difficult periods of his scientific life. Inspiration came easily. Precision did not. The mathematics fought him at every turn. He knew the structure he sought must involve the metric tensor, the mathematical object that described how distances and times were measured in curved space-time. This tensor would determine how clocks ticked and how rulers stretched or contracted, depending on their position in a gravitational field. He also knew that the curvature of space-time itself must play a role, represented by quantities known today as the Ricci curvature and the Riemann curvature tensor. These objects described how geometry deviated from flatness, how straight lines bent, and how shapes distorted. But turning these ideas into laws required a mastery of tensor calculus that Einstein did not yet possess. Marcel Grossmann became essential during this struggle. Grossmann guided Einstein through the formal mathematics with patience and clarity, helping him translate physical intuition into rigorous structure. The two worked side by side, filling notebooks with calculations, exploring every possibility the mathematics allowed. They examined how the metric tensor influenced geodesics, the natural paths that objects follow in curved space-time. They studied how curvature should depend on mass and energy, ensuring that the theory reduced smoothly to Newton's gravity in the appropriate limit. Every step had to be precise. Every equation had to be consistent with observation. During these years, Einstein often doubted himself. He produced versions of the gravitational field equations that looked promising, but ultimately failed to satisfy essential requirements. In some cases, the equations did not conserve energy. In other cases, they did not align with known astronomical measurements. The mathematics was unforgiving. Each failure weighed on him, yet he refused to abandon the principle that guided his efforts. If gravity and acceleration were equivalent, then falling objects must follow natural paths determined solely by space-time's curvature. This conviction gave Einstein the determination to press forward. Gradually, the structure of the theory began to crystallize. Einstein recognized that the gravitational field must be encoded in the metric itself, and that the curvature derived from that metric must be linked directly to the distribution of matter and energy. He understood that the geometry of space-time could not exist independently. It had to respond to the presence of mass. Heavy bodies like stars and planets would distort the geometry around them, shaping the paths of objects and beams of light. This dynamic relationship between matter and geometry became the heart of general relativity. As the mathematics grew clearer, so did the physical consequences. The new theory predicted that a beam of light passing near a massive object would bend, not because light possessed mass, but because space-time itself curved along the path. Einstein calculated the amount of bending and found that it differed from the value predicted by Newtonian approximations. This offered a direct and measurable test, one that could confirm or refute the theory. He also examined the behavior of clocks in gravitational fields, discovering that time would flow more slowly near massive bodies. This gravitational time dilation was a radical prediction, yet it followed inevitably from the equations. Even the long-standing mystery of Mercury's anomalous orbit emerged naturally from this curved space-time picture. Einstein calculated the extra precession, and match the observed 43 arc-seconds per century precisely. These successes told him he was close, but the mathematical structure still resisted final form. For months, in 1915, Einstein revisited and revised the equations repeatedly. He delivered a series of lectures in Berlin, each one representing a step closer to the truth. Week after week, he refined the tensors, corrected earlier mistakes, and tightened the mathematical connections. At last, in late November of that year, he arrived at the equations that unified geometry and gravitation. The formulation linked the curvature of spacetime to the energy and momentum of matter. In one stroke, Einstein provided a new foundation for physics. The publication of these field equations marked the moment when general relativity became a complete theory. It had taken years of effort, deep intuition, and a willingness to step beyond the familiar boundaries of classical physics. The result was a new way of seeing the universe. Space was no longer a static backdrop. Time was no longer a universal rhythm. Gravity was no longer an instantaneous force. Instead, the universe became a dynamic, flexible fabric, shaped by the energy within it. Objects moved not because they were pushed or pulled, but because they followed the natural curves of space-time. Einstein had climbed the mountain that had loomed before him for a decade, but now he stood before a new challenge. A theory this bold demanded testing. Predictions were ready. Observations awaited. Nature would decide if this new picture of gravity belonged among the great scientific truths. Einstein emerged from the winter of 1915 with a theory unlike anything physics had ever seen. The equations he had uncovered were elegant yet immense in their meaning. They declared that mass and energy told space-time how to curve, and space-time told matter how to move. For centuries, gravity had been understood as a force acting across empty space. Now it became the shape of space and the rhythm of time themselves. Yet the world would not accept such a profound shift based on mathematical beauty alone. The new theory needed proof. The universe would have to speak. Einstein knew exactly where to listen. For generations, astronomers had puzzled over Mercury's orbit. Its perihelion drifted slightly more than Newton's gravity could explain. The discrepancy was tiny, but relentless. If general relativity were correct, its geometry should produce an extra shift precisely equal to the stubborn 43 arc-seconds per century. Einstein performed the calculation with tense anticipation, tracing the motion of a planet moving through curved space-time instead of a flat Newtonian stage. When he finished, the number matched perfectly. It was as though Mercury had been waiting all along for someone to understand the message written in its orbit. The match was so exact that Einstein reportedly felt a surge of emotion. After 10 years of searching, he knew he had found the right path. Still, one success was not enough. The bending of starlight offered a second test. Newtonian physics, when adapted to treat light like a stream of particles, predicted a small deflection as starlight passed near the sun. But Einstein's theory, with its curved space-time, predicted a value nearly twice as large. This difference created a rare opportunity. During a total solar eclipse, when the sun's glare vanished, starlight passing near the solar limb could be photographed and measured. If the bending matched Einstein's prediction, the universe would affirm his vision. If it matched the Newtonian estimate, general relativity would collapse. The next suitable eclipse would not occur until 1919. Einstein could only wait, hoping the sky would cooperate. In the meantime, he continued exploring the consequences of his equations. The new theory predicted gravitational redshift, an effect where light climbing out of a gravitational field would lose energy and shift toward redder wavelengths. It predicted gravitational time dilation, where time slowed near massive bodies. It predicted that objects in free fall followed geodesics, the natural curves of space-time. Each prediction added a new layer to the theory's depth. Each one waited for future generations to test. Einstein also recognized something remarkable. His equations contained Newton's gravity within them. When gravitational fields were weak and velocities were low, the curved space-time picture flattened into the Newtonian world. The inverse square law emerged naturally as an approximation. Newton's universe was not wrong. It was simply a limited view, like a map of Earth that appeared flat because the surface curvature was too small to detect on a local scale. Relativity did not erase Newton. It revealed why Newton had been so successful and why he had reached his limits. As Einstein refined the theory, he sensed that he had touched something deeper than a new law of physics. He had uncovered a structure hidden beneath the familiar world, a structure where geometry became dynamic and where time became malleable. Yet he also knew that no theory, no matter how profound, could stand without evidence. While he waited for observational confirmation, he prepared for the possibility that nature might have other plans. The Eclipse expeditions were daring. Weather could intervene. Equipment could fail. The results could be ambiguous. But Einstein understood that science advances not by certainty, but by courage in the face of uncertainty. During these months, the scientific community reacted with a mixture of curiosity, skepticism, and admiration. Some found the mathematics overwhelming. Others doubted that space and time could bend. A few worried that the theory might be too radical to accept. But those who studied the equations closely sensed their depth. The theory had a coherence and clarity that set it apart from other attempts to modify Newtonian gravity. It was not a patch or a correction. It was a fundamentally new way of understanding the universe. By the time the Eclipse expedition set out, the stage was set for a moment that would define 20th century science. If the stars near the sun shifted in the sky by the amount Einstein predicted, the universe would be revealed not as a flat stage, but as a curved fabric shaped by mass and energy. Gravity would be transformed from a force into a feature of space-time, and the world would witness the rise of a theory that explained the structure of the cosmos with unmatched clarity. The moment of truth was approaching. The next chapter would unfold not in equations, but in the sky itself, where starlight and shadow would test the ideas that had taken Einstein a decade to build. Long before Einstein's equations reshaped the foundations of physics, astronomers had been watching a quiet irregularity unfold in the inner solar system. Mercury, the swiftest of the planets, traced an orbit that was almost perfect, yet carried within it a small, persistent whisper that something deeper was happening. Each time Mercury swung closest to the Sun, that point shifted ever so slightly, drifting forward along its orbit. To the unaided eye, this change was invisible, but through generations of careful observation, the drift became a number etched into astronomical history. Throughout the early 19th century, Astronomers refined their instruments and gathered increasingly precise measurements of Mercury's motion. They charted its path across the sky, tracked its position relative to the Sun, and calculated the slow rotation of its elliptical orbit. This rotation, known as perihelion precession, was expected. Every planet experiences it because each planet pulls on the others, subtly reshaping their orbits over time. Newton's gravity predicted most of the effect with remarkable success, but not all of it. When all known influences were included, a small remainder remained unexplained. Mercury advanced 43 arcseconds per century, more than Newton's theory could justify. The anomaly was so small that it demanded extraordinary precision to detect. But once detected, it refused to vanish. Astronomers repeated the calculations. They double-checked observations. They examined possible errors in the masses of planets and the effects of their gravitational pulls. They refined measurements of the Sun's shape, wondering whether the star's rotation might distort its gravitational field enough to account for the discrepancy. But no matter how carefully they adjusted the known factors, the stubborn remainder persisted. Urbain Le Verrier, the brilliant mathematician who had earlier predicted the existence of Neptune using Newtonian principles, turned his attention to the puzzle. He recalculated Mercury's orbit and confirmed that the anomaly was real. His success with Neptune had shown the power of Newton's gravity to reveal unseen worlds. So he wondered whether another hidden object might be tugging at Mercury. He proposed an intramercurial planet, a small world orbiting even closer to the Sun. If such a planet existed, it could add the missing gravitational pull. Le Verrier named this hypothetical body Vulcan. Astronomers searched for it eagerly. Solar eclipses offered the best chance to spot a faint object near the Sun. During these brief windows, the Sun's brilliance dimmed, revealing stars and planets usually invisible. Observers pointed telescopes toward the solar limb, hoping to glimpse the elusive world. Some reported possible sightings, but none were consistent. None were repeated. As the years passed, the idea of Vulcan began to fade. The sky offered no confirmation, yet the anomaly remained. The universe had presented a number that refused to fit. Newton's law, which had guided physics since the 17th century, faltered in the presence of this whisper from Mercury. Scientists hesitated to draw drastic conclusions. Newton's gravity had succeeded too brilliantly, too universally, to be discarded lightly. For more than 2 centuries, it had predicted planetary motion, explained tides, guided navigation, and revealed Neptune. A theory of such achievement deserved respect. The goal was not to overthrow it. The goal was to understand why one small planet near the Sun refused to obey it completely. Throughout the second half of the 19th century, the anomaly remained a quiet source of discomfort. Astronomers continued refining their measurements. They searched tenaciously for Vulcan, hoping to restore harmony to the Newtonian universe. But the evidence refused to align. The Sun was not misshapen enough. No hidden planet appeared. No measurement error explained the discrepancy. The conflict grew sharper as instruments improved. With each refinement, the 43 arcseconds per century stood firm, a precise and unyielding reminder that the universe contained subtleties beyond Newton's reach. When Einstein introduced General Relativity, Mercury's orbit became an immediate testing ground. If spacetime curved near the Sun, as Einstein's equations insisted, then the path of Mercury should shift accordingly. He calculated the effect with intense focus, tracing how the curvature created by the Sun's mass would alter the orbit. The result matched the anomaly exactly. The missing 43 arcseconds did not come from an unseen planet or a flaw in measurement. They came from the geometry of space-time itself. Newton had drawn the outline. Einstein revealed the hidden depth. The resolution of Mercury's puzzle did more than confirm a prediction. It marked the moment when general relativity stepped from elegant mathematics into physical reality. A problem that had resisted explanation for decades yielded instantly to the curvature of space-time. The universe had spoken clearly. The old law was not wrong, it was incomplete. The new theory honored its successes while revealing what lay beneath. The triumph over Mercury's anomaly transformed a quiet irregularity into a profound confirmation of Einstein's vision. But the next test would be far more dramatic. It required precise measurements under extraordinary conditions. It required darkness, starlight, and the moon aligning perfectly with the sun. The story of Mercury's orbit did not end with the realization that Newton's gravity could not fully explain it. Instead, the anomaly became a beacon pointing toward a deeper structure in the universe, a structure Einstein believed he had uncovered. But a single success, no matter how precise, was not enough to convince the scientific world to embrace such a radical transformation. The stakes were enormous. Newton's theory had guided physics for centuries. Replacing it required evidence so striking and so clear that even its most devoted defenders would have to listen. Einstein understood that astronomy would provide this next test. The universe offered a rare opportunity in the ordinary flow of celestial motion. If space near the sun curved under the weight of the star's mass, then starlight passing close to the solar surface should bend. Newtonian physics, when forced into a prediction by treating light like tiny particles with negligible mass, produced a certain value for this deflection. Einstein's theory, however, produced nearly double that amount. The difference was not subtle. It could be measured. But the sun's overwhelming brightness made such a measurement impossible under normal conditions. Only during a total solar eclipse, when the sun's light was briefly extinguished, would the stars near its edge become visible. This rare alignment meant astronomers had to wait patiently for the sky itself to cooperate. The opportunity came with the eclipse of 1919, an event that would pass across parts of Africa and South America. Teams of astronomers prepared months in advance, packing heavy equipment into weather-dependent expeditions with no guarantee of success. Clouds could ruin everything. A lens could fog. A mechanical failure could destroy years of planning. Yet the chance to test one of the most daring predictions in scientific history was too important to ignore. The world's understanding of gravity hung in the balance. As preparations continued, general relativity remained a subject of curiosity and skepticism. Many physicists found the mathematics overwhelming. Others questioned whether space and time could truly bend, or whether Einstein's ideas were too abstract to describe real physics. Newspapers occasionally mentioned his strange new theory with a mixture of intrigue and caution. But for Einstein, the eclipse represented something far more personal. It was the moment when nature would answer the question that had driven him for years. Was the universe shaped by geometry, Or was Newton's instantaneous pull still the master truth? Meanwhile, astronomers revisited the details of Mercury's orbit, reassured that the match between observation and Einstein's calculation was not coincidence. The 43 arc-seconds per century had resisted every explanation rooted in classical physics, and now curved spacetime provided the missing piece with absolute precision. The success strengthened Einstein's confidence, but also intensified the pressure. A single triumph could be dismissed. Two would be far harder to ignore. If starlight bent by the predicted amount during the eclipse, the case for general relativity would become undeniable. The world waited as the eclipse drew closer. Two major expeditions set out. One team, led by Arthur Eddington, traveled to the island of Principe off the western coast of Africa. Another team journeyed to Sobral, in Brazil. They carried telescopes, photographic plates, calibration charts, and an unwavering determination to measure the subtle bending of starlight as it grazed the darkened solar limb. Months of preparation distilled into minutes of totality. As the day approached, anticipation mixed with anxiety. Clouds could erase everything in an instant. Eddington knew that success depended not only on scientific readiness, but on weather beyond any human control. Meanwhile, the Sobral team faced uncertainty with their equipment. Every variable mattered. The alignment of the moon and sun was flawless, but the world beneath them remained unpredictable. Back in Europe, Einstein waited with a patience shaped by years of struggle. He had refined general relativity through setbacks, doubts, and extraordinary labor. He understood that experimental confirmation would transform his theory from an ambitious idea into a new foundation for physics. Yet he also accepted that the universe would offer its answer in its own way. His calculations were complete. The test belonged to the sky. When the eclipse finally arrived, the moon slid silently across the sun, turning day into night for a few precious moments. Cameras clicked, plates exposed. The positions of distant stars, hidden on ordinary days, suddenly appeared like faint precious marks against a darkened sky. The data was captured, fragile and irreplaceable, carried home with careful hands. Even before the plates were analyzed, astronomers sensed that they had witnessed something historic, but only through meticulous examination would the truth emerge. Were the stars displaced by Newton's prediction or Einstein's? Had space near the sun bent as his equations insisted? Or would the old theory reassert itself one final time? As the world waited, the future of gravity hung in the delicate silver grains of photographic glass. The deeper shape of the universe was written there, waiting to be revealed. The photographic plates returned from Principe and Sobral carried within them the faint traces of stars, whose light had skimmed the edge of the sun during the brief darkness of the eclipse. Each tiny dot of silver grains held the potential to confirm or deny one of the most daring ideas ever proposed in physics. Yet the plates themselves did not reveal their meaning immediately. Their message had to be coaxed out through careful comparison, measurement, and analysis. The bending of starlight was not dramatic. It was subtle, delicate, a shift measured in tiny fractions of a degree. Only patience and precision could reveal the truth. Arthur Eddington approached the task with the calm determination that had carried him through the uncertainties of the expedition. He knew that controversy surrounded Einstein's theory. Some scientists viewed general relativity with cautious interest. Others dismissed it as too radical. But Eddington had studied Einstein's equations closely. He understood their logic, their beauty, and their necessity. If the universe obeyed the rules of special relativity, then gravity could not remain as Newton had described it. The shape of spacetime had to play a role. Eddington believed the eclipse might reveal that deeper structure. At the same time, he was fully aware of the responsibility that rested on his measurements. The plates from Principe were affected by clouds, blurring some of the images. The plates from Sobral appeared clearer, but the equipment there had experienced complications that introduced uncertainties of their own. Every mark on every plate had to be examined with painstaking care. Each star's position during the eclipse had to be compared with its position in the same region of the sky under normal conditions. Only the difference between the two would show whether space-time had curved. As the analysis progressed, patterns began to appear. The stars nearest the Sun did not lie exactly where they should have been. They were shifted outward, away from their expected Newtonian positions. The amount of bending was greater than the classical prediction. It aligned instead with the value that Einstein had calculated, approximately 1.75 arcseconds. The shift was small, but its meaning was enormous. It matched the geometric curvature predicted by General Relativity. Even before the results were finalized, Eddington sensed that the universe had spoken. The plates told a story that no theoretical argument alone could write. When the measurements were complete, they confirmed the bending of starlight at precisely the amount Einstein's equations required. The theory had passed its most dramatic test. The curvature of spacetime was not a mathematical abstraction. It was written in the sky, carved into the paths of photons, revealed in the quiet glow of distant stars. When the findings were presented later that year, the scientific world felt a seismic shift. Newspapers declared that Newton's laws had been overturned, though the truth was more nuanced. General relativity did not erase Newton. It encompassed him. It explained why his theory worked so well in most circumstances, and why it failed under the extreme conditions near the Sun. Einstein's ideas were greeted with a mixture of wonder and skepticism, but the evidence was too strong to ignore. Space and time had become dynamic participants in the universe, bending and stretching under the influence of mass and energy. In the years that followed, further scrutiny confirmed that the eclipse results were robust. New measurements, improved equipment, and refined methods all supported the conclusion that starlight bent as it passed near the Sun. What began as a daring prediction had become a verified feature of nature. The sky itself had affirmed the geometry of Einstein's universe. The success of the eclipse expedition was more than a scientific milestone. It was a turning point in human understanding. The cosmos was no longer a stage where forces acted across emptiness. It had become a woven fabric where gravity emerged from curvature, where light followed the contours of space-time, and where the universe revealed its structure through patterns only geometry could describe. But this was only the beginning. The bending of starlight was the first major confirmation of general relativity, yet many more tests awaited. Some would unfold high in mountain laboratories. Others would take place in aircraft circling the Earth. Some would reveal themselves through the steady pulse of distant stars. The next chapter of the story would show how gravity shaped time itself, slowing its flow in ways that would soon be measured with remarkable precision. The morning of the eclipse arrived with the quiet tension of a moment that could reshape the world. Across Principe and Sobral, the sky held its breath as teams of astronomers prepared their instruments, each aware that the next few minutes would test a theory daring enough to redefine the nature of gravity itself. General Relativity had already solved Mercury's lingering puzzle, but that triumph lived in calculations and theory. The bending of starlight would live in the sky, in the raw and unforgiving precision of nature. If Einstein's prediction was correct, the universe would reveal its hidden geometry. If not, the decade he spent rebuilding gravity from the ground up would collapse beneath the weight of a single observation. As the moon began its slow passage across the sun, the world beneath darkened into an eerie twilight. Shadows deepened, air cooled, animals quieted in confusion. The sun's outer atmosphere flared in a pale crown of light. Against this brief and otherworldly backdrop, stars that were normally washed away by the sun's glare awakened, faint but visible. They became the silent witnesses of an experiment that stretched from Earth to the far reaches of spacetime. Their positions on the photographic plates would reveal whether the universe bent light as Einstein claimed, or whether Newton's shadow still ruled the sky. On the island of Principe, Arthur Eddington adjusted his equipment with practiced calm, though clouds threatened to obscure the event. The sky above him wavered between clarity and uncertainty. His telescopes waited, aimed precisely at the region of sky where stars hid behind the sunlight on ordinary days. For Eddington, this moment carried both scientific and personal significance. He had long believed that Einstein's theory contained the seeds of a deeper truth, and he felt a duty to ensure the test was carried out with unwavering care. In Sobral, across the ocean in Brazil, the second team prepared their own instruments. Their sky was clearer, though their equipment had encountered challenges, leaving the outcome uncertain until the very last moment. Both sites represented the full commitment of the scientific community to a question nearly unimaginable a generation earlier. Could spacetime itself bend? Could light, the messenger of the cosmos, follow a curved path carved by the gravity of the sun? When totality arrived, the world momentarily stepped outside its familiar rhythm. Darkness fell at midday. The sun vanished behind a perfect lunar disk, and the stars near its edge flickered into view. Telescopes captured their faint images, each exposure holding a clue to the shape of spacetime. In those short minutes, the plates recorded what no human eye could see unaided. The entire experiment relied on tiny shifts in the apparent positions of stars, displacements measured in arc-seconds yet monumental in meaning. When the light returned and the plates were secured, the true work began. The raw images held no immediate revelation. They had to be compared with reference plates taken when the sun was elsewhere in the sky. The positions of stars on the eclipse plates had to be matched with their ordinary locations. Only by comparing the two could astronomers measure the tiny bending predicted by Einstein. Magnifying lenses were positioned. Rulers and grids were aligned. Every mark had to be traced with absolute precision. Even the slightest misalignment could distort the results. Eddington worked with quiet intensity, sifting through the blurred, cloud-touched Principe plates. Despite their imperfections, they contained enough information to reveal a trend. The stars closest to the Sun appeared displaced outward. Space near the Sun was not straight, it curved. This was not speculation, it was measurement. The Sobral plates told a similar story, though some of the equipment had introduced uncertainties that required careful correction. Yet even with these challenges, the stars had shifted by an amount remarkably close to Einstein's value of 1.75 arcseconds. As the analysis continued, the conclusion grew unmistakable. The universe had followed Einstein's geometry. Light had bent through curved space-time, exactly as the equations demanded. Newton's predicted deflection, roughly half as large, was nowhere to be seen in the data. The sky had chosen. When the results were announced, they echoed across the world. Newspapers carried headlines declaring the triumph of a new science. Einstein's name, once known only to physicists, spread across continents. Yet behind the excitement lay a deeper truth. General Relativity had not merely passed a test. It had revealed a universe far more dynamic and intricate than the one humanity had imagined. Space could bend. Time could curve. Light could follow paths shaped by the presence of mass. The bending of starlight marked the moment when general relativity stepped beyond mathematics and entered the world of observation. But this was only the beginning. The next chapter of gravity would unfold not through distant stars, but through clocks, laboratories, mountaintops, and satellites orbiting Earth. Time itself would soon reveal its dependence on gravity, proving that the fabric of the universe was even stranger than curved space alone could suggest. The confirmation of starlight bending rippled through the scientific community. But for Einstein, the eclipse was not the end of a journey. It was the beginning of a new era. If gravity could shape the path of light, then it could shape the flow of time itself. This realization carried implications that stretched far beyond the sun and distant stars. It reached into the workings of clocks, the rhythms of daily life, and the unseen layers of reality woven into the passage of seconds. The universe had revealed that space could curve. Now it would reveal that time could stretch. Einstein understood that if mass could warp space-time, then clocks in stronger gravitational fields would tick more slowly than clocks farther away. This was not an optional detail. It was a direct and unavoidable consequence of the geometry encoded in general relativity. Near a massive body, time itself must pass at a different rate. Yet when Einstein first proposed this idea, there was little evidence that anyone could ever measure such an effect. The differences were far too small for the instruments of his time. But science advances through precision. And as the 20th century unfolded, humanity learned to measure time with a sensitivity that earlier generations could not imagine. Before those technological revolutions arrived, astronomers and physicists considered the implications of this strange prediction. If time passed more slowly near the surface of Earth than atop a distant mountain, then the universe was far stranger than classical physics ever suggested. Time was not absolute. The universe did not share a universal clock. Every height, every mass, every gravitational field sculpted time in its own subtle way. These ideas sounded almost philosophical, yet they arose from equations that had already proven themselves through the bending of light and the motion of Mercury. As scientists explored these predictions, they recognized that the universe offered small but measurable opportunities to detect gravitational time dilation. The challenge lay in creating a device precise enough to reveal the effect. Standard mechanical clocks could never approach the necessary sensitivity, but the development of atomic clocks, with their extraordinary stability and precision, changed everything. Time could now be measured not by gears or springs, but by the vibrations of atoms, oscillations so regular that even tiny shifts revealed the influence of gravity. Long before satellite navigation systems relied on relativity, physicists realized that shifts in frequency or wavelength could serve as windows into gravitational time dilation. Photons climbing upward through Earth's gravitational field would lose energy, shifting to longer wavelengths. This effect, known as gravitational redshift, was another direct prediction of general relativity. The universe had already provided clues to its presence. Light-escaping massive stars displayed redshifts slightly greater than expected, though these observations remained imprecise. A controlled experiment on Earth would provide cleaner evidence. The idea of testing these predictions in laboratories felt ambitious, but the scientific community was no longer hesitant to challenge the boundaries of measurement. The success of the Eclipse observations emboldened researchers. If spacetime could bend starlight, then laboratories on Earth could reveal the more delicate features of gravitational influence. The world had entered an age where precision was not merely a tool, but a gateway to deeper truths. As the decades passed, researchers began designing experiments to measure gravitational redshift directly. They carefully considered how to manipulate radiation, how to compare clocks at different heights, and how to isolate the minute effects of Earth's gravity. The development of the Mercury effect, which allowed gamma rays to be emitted and absorbed without energy loss from atomic recoil, opened the door to an experiment of extraordinary sensitivity. With this technique, physicists could detect energy shifts equivalent to tiny changes predicted by gravitational redshift. The stage was set for one of the most delicate experiments in the history of physics, one that would soon show that time itself could be pulled, stretched, and slowed by gravity. The bending of light had revealed the curvature of space. The next discovery would reveal the curvature of time. The experiment that would reveal gravity's grip on time unfolded not on a distant mountain or in the depths of space, but inside a tower in Cambridge, Massachusetts. In the late 1950s, Robert Pound and Glenn Rebka set out to measure an effect so subtle that even Einstein once wondered whether humanity would ever detect it. They aimed to observe the gravitational redshift of light over a vertical height of only a few tens of meters. According to General Relativity, photons climbing upward through Earth's gravitational field should lose an almost impossibly tiny amount of energy. Their wavelength should stretch by a minuscule fraction. Time itself, measured through the frequency of the photons, should reveal the influence of gravity. To detect this effect, Pound and Rebka used the Mercury effect, which allowed atoms in solid materials to emit and absorb gamma rays without losing energy to recoil. This created photons of extraordinary purity, whose frequencies could be compared with unmatched precision. They placed a gamma ray source at the bottom of the Jefferson Physical Laboratory Tower at Harvard University and a detector at the top. If general relativity was correct, the photons that reached the top would be slightly redshifted, arriving with a frequency a tiny bit lower than when they left the bottom. Even with these tools, the experiment required exquisite care. Vibrations, temperature changes, and even subtle motions of the building could disrupt the measurement. Pound and Rebka compensated for these effects by moving the source back and forth with controlled precision, tuning the system until they could detect the minute shift in energy. After weeks of careful measurements, the predicted redshift emerged unmistakably. It matched Einstein's equations exactly. Gravitational time dilation, once a theoretical curiosity, had become a measurable feature of everyday physics. This result marked a turning point. No longer was gravitational time dilation confined to astronomical speculation. No longer was it a prediction awaiting confirmation. It was a documented part of the world, detectable across a vertical span barely wider than a staircase. Time itself slowed in stronger gravitational fields and flowed faster at greater heights. The bending of time was real. The discovery opened the door to even more dramatic tests. In 1971, Joseph Haffel and Richard Keating carried atomic clocks aboard commercial aircraft, flying one set eastward and another westward around Earth. When the clocks returned, they no longer agreed. The eastward flying clocks had lost time. The westward flying clocks had gained it. These shifts were exactly what relativity predicted, combining the effects of motion and gravity. Time dilation had become a global experiment, measurable across the sky. As atomic clocks improved, scientists placed pairs of them at different altitudes, mountain observatories and sea-level laboratories. The clocks disagreed by precisely the amount general relativity predicted. Even a height difference of a few dozen centimeters was enough for the most advanced clocks to detect the slowing of time. Gravity shaped time with the same quiet precision that bent the paths of planets and starlight. And this slowing of time was not just a scientific curiosity. It became essential to one of modern civilization's most widely used technologies. Satellite navigation systems relied on clocks orbiting high above Earth, where gravity was weaker and time moved faster. Without continuous relativistic corrections, the system would drift by kilometers each day, rendering navigation impossible. The quiet mathematics Einstein developed decades earlier turned out to be indispensable for guiding ships, airplanes, and smartphones. General relativity had become part of daily life, quietly shaping the modern world. Each experiment, Pound and Rebka's tower, Haffel and Keating's flights, the careful comparisons of atomic clocks across altitudes revealed the same truth. Gravity was not just a force that shaped the motions of planets. It shaped the flow of time. Space-time was not an abstract idea. It was the living structure of the universe, measurable with instruments, detectable in laboratories, essential to human technology. The bending of light had shown the curvature of space. The slowing of clocks showed the curvature of time. The evidence for general relativity now stretched from the eclipse shadows of 1919 to the ticking of atomic clocks in orbit. Step by step, the universe had confirmed Einstein's vision, but still deeper mysteries awaited. In the decades that followed, astronomers would turn their gaze toward objects so dense, so extreme, and so powerful that they seemed to defy imagination. General relativity predicted their existence long before anyone observed them. These objects would test gravity in its most intense form, far beyond anything seen in the solar system. Long after the Eclipse expeditions confirmed that space-time could bend the path of light, Einstein's theory continued to reveal consequences that were even more profound. If gravity shaped the geometry of space, then it must also shape the rhythm of time. This idea was woven directly into the mathematics of general relativity. Near a massive body, clocks would slow. Far from that body, time would run more quickly. To Einstein, this was as natural as the curvature of space itself. To the rest of the world, it was nearly unimaginable. Gravity, the familiar pull that guided falling apples and orbiting moons, now reached into the very flow of moments. For decades, the idea remained difficult to test. Clocks were not yet precise enough. Instruments drifted. Mechanical gears wavered. Even as general relativity gained acceptance, gravitational time dilation seemed destined to remain a theoretical insight rather than a measurable reality. But as the 20th century progressed, new technologies emerged. Atomic clocks began to tick with astonishing regularity. Their frequencies were so stable that even the slightest change in gravitational potential would shift their rhythm. Time was no longer an abstract measure. It was a measurable signal, sensitive to the curvature of space-time. Physicists understood that Earth offered a natural laboratory for detecting gravitational time dilation. The surface of the planet sat deep within a gravitational well. A mountaintop, though only a few kilometers above sea level, lay measurably higher in potential. According to general relativity, clocks at altitude should run faster. Clocks near sea level should run slower. For most of history, the difference was far too small to detect. Now it was within reach. In the 1950s, long before satellites filled the sky, researchers began planning experiments to probe these predictions. Their challenge was immense. They needed to isolate gravitational effects from the countless sources of error that could distort the results. Temperature changes, vibrations, electrical noise, and imperfections in timing instruments could all mask the tiny shift in frequency caused by gravity. But the growing precision of atomic clocks made physicists optimistic. They believed time could be used as a tool to listen to gravity itself. By the late 1950s, Robert Pound and Glenn Repka designed the experiment that would bring this prediction into clear focus. They turned to the Mossbauer effect, which produced gamma rays of extraordinary purity, emitted and absorbed without the energy losses that normally blurred such measurements. If gravitational redshift existed, the gamma rays emitted at the bottom of a tall tower should arrive at the top with slightly less energy. This change was tiny, far smaller than anything classical instruments could detect. But with the Mossbauer effect, it became measurable. Pound and Repka placed their gamma ray source at the base of the Jefferson Laboratory Tower at Harvard and positioned a detector at the top. By slowly moving the source, they compensated for known sources of error and brought the system into tune. Then they measured the energy difference between the emitted and received photons. When the results finally stabilized, the shift matched Einstein's prediction with remarkable precision. Light had lost energy climbing upward. Time at the bottom of the tower ran slightly slower than time at the top. Gravity had revealed its influence on time itself. This experiment marked a turning point. The bending of light had shown the curvature of space. The redshift of photons now showed the curvature of time. Einstein's theory was no longer a description of distant astronomical events alone. It had become a practical, testable part of physics on Earth. With the spread of atomic clocks, even more precise tests became possible. Clocks carried aboard aircraft confirmed that both motion and gravity affected time. Clocks stationed at mountaintops and sea level drifted apart at precisely the rates predicted by general relativity. Every improvement in timing technology tightened the agreement between theory and observation. And then came satellites. High above Earth, in orbits where gravity was weaker, clocks ticked faster than their counterparts on the surface. Engineers designing the satellite navigation system understood that these differences could not be ignored. Without continuous relativistic corrections, navigational signals would drift and the system would fail. General relativity, once a theory born from abstract geometry, became essential for guiding ships, airplanes, and every device that depended on global positioning signals. Time itself had become a window into the structure of space-time. With each experiment, the universe confirmed that gravity was not merely a force. It was the shape of time and space, a living geometry that touched every corner of reality. The next mystery awaited in places where gravity grew unimaginably intense, where space-time curved so sharply that even light could not escape. The realization that gravity shaped time opened a path toward experiments that pushed precision to extraordinary limits. Once scientists understood that clocks at different heights ticked at different rates, they began searching for ways to measure the effect with even greater accuracy. Every improvement in timing technology transformed what once seemed impossible into a test within reach. As atomic clocks became more stable, the predictions of general relativity grew not only testable, but essential to the way modern science and technology functioned. By the 1960s, physicists recognized that gravitational time dilation could be explored not only through the redshift of photons, but through the direct comparison of clocks themselves. Atomic clocks, which relied on the frequency of atomic transitions rather than mechanical movement, provided a stability that surpassed any earlier timekeeping device. These clocks were so precise that the difference in time between two of them, separated by just a small change in height, could eventually be detected. Time was becoming a measurable terrain, rising and falling with the curves of space-time. But before these time comparisons reached their modern levels of sensitivity, one landmark test took shape in the skies above Earth. In 1971, Joseph Haffel and Richard Keating prepared an experiment that would take relativity out of towers and laboratories and lift it into the global arena. They transported highly accurate cesium beam atomic clocks onto commercial aircraft and carried them around the world. One set of flights circled eastward, moving in the direction of Earth's rotation. The other circled westward, moving against it. General relativity predicted that the clocks would not agree when they returned. The aircraft flying eastward, moving faster relative to Earth's center, would experience a combination of gravitational and velocity effects that caused its clocks to lose time. The westward flight would experience a different combination of these effects, causing its clocks to gain time. The differences were extremely small, measured in nanoseconds, but the atomic clocks were sensitive enough to detect them. When the flights landed and the clocks were compared, the results matched Einstein's predictions. Time had flowed at slightly different rates for each journey. The rhythms of seconds themselves had bent under the combined influences of gravity and motion. For the first time, relativity had been tested on a planetary scale. Time dilation had become something the Earth itself revealed as people moved across it, carried by engines and wings. This success encouraged even more refined experiments. Physicists placed atomic clocks at different elevations on Earth's surface, comparing clocks at mountaintop observatories with those at sea-level laboratories. The higher clocks, experiencing slightly weaker gravity, ran faster. The lower clocks, deeper in Earth's gravitational well, ran slower. As technology improved, scientists discovered that even a change of a meter in height produced a measurable difference. Time had become as local and flexible as the curvature of space. These discoveries did more than confirm the predictions of general relativity. They forced scientists to rethink how the universe operated at every scale. Time was not universal. It depended on position, motion, and the gravitational field. This understanding became essential when engineers developed the satellite navigation system. Satellites orbit high above Earth, where gravity is weaker and time runs faster. Without correcting for gravitational time dilation, their onboard clocks would drift rapidly. The navigation signals sent to Earth would become increasingly inaccurate. Within a single day, errors would accumulate to distances far too large to be useful. The system could not function without Einstein's equations. Thus, the theory that once seemed abstract and distant became part of daily life. Every time a device calculates a location, it silently depends on the warping of space-time, the slowing and speeding of clocks, and the precise corrections that general relativity demands. Time dilation is not just a scientific curiosity. It is a practical feature of the world, shaping the technology that guides airplanes, ships, cars, and every person holding a navigation-enabled device. These confirmations established general relativity as one of the most rigorously tested theories in the history of science. Yet even as laboratories and satellites confirmed its predictions in everyday environments, Einstein's equations whispered of stranger realms. They described places where gravity grew so strong that time nearly stopped, where space-time curved so sharply that ordinary intuition collapsed. These predictions pointed toward the existence of objects once thought impossible. Objects formed from the collapse of massive stars, hidden behind horizons from which no light could escape. The next chapter of Gravity would lead to the edge of these extreme worlds, where general relativity revealed some of its most astonishing consequences. As the 20th century progressed, the ability to measure time with ever sharper precision transformed the study of gravity from a matter of astronomical patience into a field grounded in laboratory certainty. Yet even as clocks revealed the quiet ways gravity shaped time on Earth, scientists began to realize that the full implications of Einstein's equations reached far beyond mountaintops, aircraft, or satellites. General relativity was not merely a theory about gentle curvatures around planets. It described the behavior of space-time under conditions so extreme that the familiar world seemed to dissolve. It pointed toward phenomena that appeared more like cosmic riddles than physical objects. Still, before scientists confronted these extreme predictions, one truth had become unmistakable. Every test of gravitational time dilation reinforced that general relativity was not a fragile construction held together by speculation. It was woven into the measurable structure of the world. Pound and Rebka had shown that light climbing a tower lost energy. Haffel and Keating had shown that time flowed differently for clocks circling the globe. Satellite navigation systems had shown that entire global networks would collapse without relativistic corrections. Each result stood independently, yet all of them pointed to the same conclusion. Gravity was not a force acting across empty space. It was the bending of spacetime, the shaping of time itself. These experiments also revealed a quiet symmetry, the same geometry that curved the paths of planets and photons also sculpted the flow of seconds. There was no separate explanation for each phenomenon. They were all manifestations of the same underlying structure. The theory predicted these effects with a precision that no alternative explanation could match. The universe, through every measurement, affirmed the connection. Whenever time seemed to stretch, whenever clocks fell out of synchrony, whenever light red-shifted or blue-shifted in the presence of mass, general relativity stood as the one explanation that fit it all. By the 1980s and 1990s, the precision of atomic clocks had advanced so dramatically that researchers could measure gravitational time dilation over distances previously considered trivial. In some laboratories, raising a clock by less than a meter produced a difference large enough to detect. Time had become a landscape, rising and falling gently with altitude, sculpted by Earth's gravity in ways that no person could feel, but every instrument could measure. These advances marked the beginning of relativistic geodesy, a new field where the very flow of time became a tool for mapping Earth's gravitational variations. Meanwhile, scientists refined tests of gravitational redshift using new techniques. Some sent atomic clocks aboard rockets to compare time at high altitude with time on the ground. Others used satellites specifically designed to test relativity. Every experiment, no matter how ambitious or delicate, returned the same message. Einstein's equations remained unshaken. These successes prepared the scientific community for the next frontier, one that Einstein himself had glimpsed within his equations, but never witnessed directly. His mathematics suggested that under the right conditions, mass could collapse into a region where space-time curved infinitely. Light would lose the ability to escape. Time would behave in ways that stretched the imagination. These objects, later named black holes, represented gravity pushed to its most extreme form. For decades, they remained theoretical predictions, mathematical consequences that seemed too strange to be real. But as observations grew sharper and technology advanced, evidence began to emerge. Stars circling invisible companions, X-ray emissions marking the presence of collapsed stellar cores. Jets of matter accelerated to nearly the speed of light. Bit by bit, the universe revealed that these extreme predictions were not abstract mathematics. They were real. And so, the study of time dilation and gravitational redshift, once focused on towers, airplanes, and satellites, had prepared humanity for a far deeper journey. The same equations that explained why clocks in orbit needed corrections would soon describe the behavior of matter spiraling into regions where space-time twisted into extraordinary shapes. General relativity had proven itself under gentle conditions. Now, it would be tested under conditions where gravity dominated the very structure of reality. The next chapter would lead directly into those extreme realms, where Einstein's equations described not just slow clocks and bent light, but the deep gravitational wells of collapsed stars and the hidden boundaries of black holes. It was here, In the strongest gravitational fields the universe could create, that general relativity would reveal some of its most astonishing predictions. By the time general relativity had proven itself through laboratory experiments, atomic clock comparisons, and satellite technologies, Einstein's equations had already been whispering about something far more extreme. Deep within their structure lay the prediction of objects so dense and so gravitationally intense that they would carve space-time into forms unlike anything the universe had previously revealed. These entities were not born from speculation, but from the mathematics of curved space-time itself. If enough mass were compressed into a sufficiently small region, the curvature would become so steep that not even light could escape. Such an object would trap both matter and radiation behind a boundary from which no return was possible. In 1916, Carl Schwarzschild, working amid the hardships of the First World War, discovered the first exact solution to Einstein's newly published field equations. His solution described the gravitational field around a perfectly spherical mass. What emerged from his calculations was a radius where the curvature of spacetime became so extreme that escape was impossible. This boundary, later named the event horizon, marked the surface beyond which information could no longer return to the universe outside. Although Schwarzschild's mathematics was precise, the idea felt almost too strange to be real. Many physicists of the era wondered whether such an object could exist in nature or whether it was merely a mathematical artifact. For decades, black holes lived quietly inside the equations, neither dismissed nor confirmed. Some scientists suspected that the collapse of massive stars might create these extraordinary objects. Others believed that extreme pressures or unknown processes might prevent full collapse, keeping nature from reaching the Schwarzschild radius. Without observational evidence, the question remained open. The universe, however, had already begun forging these extreme objects long before human beings learned to detect them. As telescopes improved and astronomers began exploring the sky in wavelengths beyond visible light, unexpected signals appeared. In the 1960s, satellites scanning the sky for high-energy radiation discovered powerful X-ray sources. One of the most striking was located in the constellation Cygnus. Named Cygnus X1, it flickered and pulsed with a pattern suggesting matter spiraling into an unseen companion. Observations revealed that the visible star in the system orbited an invisible partner with a mass too large and too compact to be anything but a black hole. Cygnus X1 became one of the first strong observational candidates, transforming black holes from theoretical curiosities into astrophysical realities. But the universe held even more dramatic examples. At the center of our own galaxy lay Sagittarius A star, a compact radio source hidden behind clouds of interstellar dust. For decades, astronomers suspected that something massive dwelled there, but the nature of that mass remained uncertain. Beginning in the 1990s, teams led by Reinhard Genzel and Andrea Ghez began observing the motions of stars orbiting the galactic center. Using advanced infrared telescopes, they tracked these stars year after year. Their paths traced tight ellipses, moving with astonishing speed around a region smaller than our solar system. The only object capable of producing such gravitational influence was a supermassive black hole, millions of times the mass of the Sun. The motions of these stars became a direct measurement of spacetime's curvature on a scale far beyond anything Einstein had imagined when he first developed general relativity. In 2020, Genzel and Ghez received the Nobel Prize for their groundbreaking observations, which provided some of the clearest evidence that supermassive black holes anchor the centers of galaxies. Even more dramatic confirmation arrived when the Event Horizon Telescope, a worldwide network of synchronized radio observatories, captured the first image of the region surrounding a black hole. In 2019, the collaboration released an image of the supermassive black hole in the galaxy M87 star. The image revealed a glowing ring of light encircling a dark central shadow, a silhouette produced by spacetime's curvature so extreme that photons were trapped in tight orbits. The shape of the ring matched the predictions of general relativity with striking accuracy. The universe had revealed the outline of a black hole for the first time, confirming Einstein's equations in one of the harshest environments imaginable. These observations marked a profound turning point. Black holes were no longer hidden inside equations. They were visible in the motions of stars, the glow of hot plasma spiraling inward, and the shadows carved from spacetime itself. General relativity had proven itself not only in the gentle gravitational fields of Earth, but in the most powerful gravitational wells the cosmos could create. Yet Einstein's theory held one more astonishing prediction waiting to be tested. If massive objects could bend spacetime, then the motion of those objects could create ripples in that fabric. These ripples would travel outward at the speed of light, carrying information about distant cosmic cataclysms. The theory predicted gravitational waves. For a century, they remained undetected, almost too faint to measure. But the universe does not hide its deepest truths forever. The idea that space-time could ripple was one of the most extraordinary consequences of general relativity. If mass and energy shape the geometry of the universe, then changes in that geometry should be able to move outward, carrying information with them. Einstein realized this in 1916, only a year after publishing the field equations. When he worked through the mathematics in regions where gravity was weak, he found that disturbances in space-time behaved like waves, traveling at the speed of light. These waves carried energy, just as ripples on a pond carry the imprint of a falling stone. But unlike water waves or sound waves, these ripples moved through the very fabric of space-time itself. For decades, however, gravitational waves remained a prediction with no experimental confirmation. They were expected to be extremely faint, stretching and squeezing space by amounts far smaller than the width of a proton. To detect them, humanity would need technological sensitivity that did not exist in Einstein's era or in the decades immediately following. Still, some physicists refused to let the idea fade. They believed that if the universe contained black holes, neutron stars, and other massive objects in violent motion, these cosmic collisions would send out gravitational waves strong enough to measure, if only the right instrument could be built. The first major attempt came from Joseph Weber in the 1960s. Weber constructed massive metal cylinders, hoping that a passing gravitational wave would make them vibrate with a detectable resonance. His instruments were bold and innovative, and for a time, it seemed he might have found something. But other researchers could not reproduce his signals, and the consensus eventually emerged that the technology was not sensitive enough. The challenge remained. Spacetime's ripples were too faint for the tools of that era to reveal. Yet the idea never disappeared. As the 20th century advanced and laser technology matured, a new approach began to take shape. If gravitational waves stretched and squeezed spacetime, then they would change the lengths of arms in a giant interferometer. A laser beam split into two paths could recombine in a way that revealed even minute differences in their travel times. If spacetime itself shifted, the pattern of the recombined light would change. This concept grew into one of the most ambitious scientific instruments ever built, the Laser Interferometer Gravitational Wave Observatory, known as LIGO. Engineers and physicists constructed two massive observatories in the United States, one in Washington and one in Louisiana. Each facility contained kilometer-scale vacuum tubes, carefully aligned mirrors, suspended optics, and lasers stable enough to detect distortions billions of times smaller than a meter. Every source of noise, seismic vibrations, thermal fluctuations, passing trucks, even distant storms, had to be suppressed. The challenge was immense. The slightest tremor could mask the signal of a gravitational wave. But after decades of effort, LIGO reached the sensitivity required to listen to the universe in a way no human instrument had ever done. The breakthrough arrived on a quiet day in 2015. Deep underground and across long vacuum arms, two detectors separated by thousands of kilometers registered the same faint, distinctive signal. It lasted less than a second. A rising tone, increasing in frequency and amplitude, then cutting off abruptly. It matched the predicted pattern of two black holes spiraling together, colliding, and merging into a single larger black hole. The final burst of gravitational energy, traveling for more than 1 billion years across the cosmos, had finally reached Earth. This event, named GW 150914, transformed gravitational waves from a prediction into a measured reality. The data matched Einstein's equations with extraordinary precision. The speed of the waves matched the speed of light. The waveform matched the model of black hole in spiral. The energy carried away matched the predictions of curved space-time dynamics. Every detail confirmed the vision Einstein had proposed nearly a century earlier. And this detection was only the beginning. In the years that followed, LIGO and its partner observatories captured dozens of events: black hole mergers, neutron star collisions, and other cosmic upheavals that had been invisible to telescopes using light alone. These measurements opened a new window onto the universe, allowing scientists to study gravity in motion, space-time in vibration, and cosmic events that had remained hidden for the entire history of astronomy. The discovery of gravitational waves marked the final experimental frontier of general relativity. Black holes, once theoretical, had become observable. Gravitational waves, once unimaginable, had become measurable. The universe now spoke in a language of space-time itself, and humanity had learned to listen. The first detection of gravitational waves opened a new frontier, but the full meaning of the discovery unfolded only in the years that followed. Einstein had predicted these waves in 1916, yet he doubted they would ever be observed. Their effects were too small, their signals too faint. The distortions they produced drowned easily beneath the noise of the Earth itself. And yet, by 2015, humanity had built instruments capable of sensing a stretch and squeeze of space-time so slight that it altered distances by less than a fraction of a proton's width. This achievement was not just a triumph of technology, it was a confirmation that the universe communicated through gravity as well as light. The signal of GW 150914 carried the signature of two massive black holes spiraling toward one another. Their orbits tightened as they emitted gravitational radiation, losing energy in the form of ripples racing outward at the speed of light. In the final moments before they merged, their motion accelerated through unimaginable extremes. Space stretched, time twisted. The frequencies of the waves climbed in a sweep of rising pitch. And then, abruptly, the signal ended. The two black holes had collided, forming a single larger black hole whose ringing space-time quickly settled into silence. The precision with which this event matched Einstein's predictions stunned the scientific world. The mass of the black holes, the energy radiated, the final mass of the merged object, even the way the waveform curved upward. Every detail agreed with the equations of general relativity. Nothing needed adjustment, nothing required correction. A century after its birth, Einstein's theory had passed one of its most extreme tests. But the story of gravitational waves did not end with a single event. Once LIGO learned to hear the universe, the sky filled with signals. One detection became many. Black holes of various sizes merged across billions of years of cosmic history. Some events revealed black holes larger than any observed before. Others showed populations that challenged earlier expectations about how stars lived and died. Each detection became a new experiment, probing conditions where gravity dominated every motion. Then came a different kind of event, one that did not involve black holes at all. In 2017, LIGO and its European partner Virgo detected gravitational waves from the collision of two neutron stars. Unlike black holes, neutron stars contain matter crushed to densities so high that atoms cannot survive. Their collision was a moment of violence written directly into space-time. The signal was weaker but longer, lasting nearly a minute. Its waves traced each orbit as the two dense stars spiraled together, revealing the geometry of matter under pressures no laboratory on Earth could create. For the first time, observatories using light saw the same event. Telescopes across the world detected a flash of gamma rays, then visible light, then fading afterglows across the spectrum. The universe had spoken simultaneously through gravitational waves and electromagnetic radiation. These signals showed how heavy elements, including gold and platinum, were forged in the cosmos. They revealed the birthplaces of some of the universe's rarest materials and confirmed that neutron star collisions played a crucial role in shaping cosmic chemistry. As detections multiplied, a new field emerged. Gravitational wave astronomy became a bridge between mathematics and observation, linking Einstein's geometry to the most violent events in the universe. Each new signal tested general relativity in regimes of gravity far stronger than anything accessible in the solar system. With every test, the theory held firm. The speed of the waves matched the speed of light with astonishing accuracy. Their polarization matched Einstein's predictions. Their waveforms followed the structure of curved spacetime exactly. General relativity had survived every challenge: planetary motions, bending light, slowing time, collapsing stars, and now the trembling of spacetime itself. The universe had confirmed that Einstein's equations describe its fabric not only in gentle conditions, but in the most extreme realms imaginable. Yet even as these discoveries cemented general relativity's success, they also pointed to questions still unanswered. Black holes existed, gravitational waves existed, but Newton's gravity had not been discarded. It lingered within Einstein's theory, emerging naturally whenever gravity was weak and motion slow. Most of everyday life still obeyed Newton. Engineers still used Newton's laws. Astronomers still relied on them for many calculations. General relativity did not erase the old theory. It embraced it, placing it within a wider and deeper structure. The next chapter would explore this relationship, revealing how Newton's gravity remained woven into Einstein's universe, preserved within the equations that had reshaped the cosmos. For a century, gravitational waves lived at the edge of imagination, predicted by Einstein's equations, yet hidden beneath the noise of the world. They were the faintest tremors in the fabric of space-time, ripples created when massive bodies moved with violent acceleration. Unlike light, which could be blocked or scattered, gravitational waves pass through matter almost untouched. They moved silently, carrying information about cosmic events far beyond the reach of telescopes. But their very ability to slip through the universe undisturbed made them nearly impossible to detect. If humanity wished to hear these ripples, it would need instruments capable of measuring changes in distance so small they seemed beyond the reach of technology. Einstein himself doubted that gravitational waves would ever be observed. The distortions they produced were unimaginably tiny. If two massive black holes collided in a galaxy millions of light-years away, the waves reaching Earth would stretch and squeeze space-time by amounts smaller than a fraction of a proton's width. Even the slightest vibration, footsteps, passing trucks, distant ocean waves, shifting soil, would drown the signal. In 1916, when Einstein first derived the existence of these waves, the idea of detecting them felt closer to fantasy than experiment. Yet the equations insisted they were real. If gravity shaped space-time, then changes in the mass distribution of the universe must send ripples outward. For decades, physicists debated whether these waves carried energy or whether they were merely mathematical illusions. Eventually, theoretical work clarified that gravitational waves were physically meaningful, but theory alone could not settle the question. Instruments were needed. And so, in the 1960s, Joseph Weber embarked on a daring attempt to build detectors capable of sensing these ripples. He constructed massive cylindrical bars of aluminum, hoping that a passing gravitational wave would cause them to resonate with a measurable vibration. Weber believed he had observed signals, but no other researcher could reproduce them. Although his results did not hold, he had opened a door that future generations would walk through. As technology advanced, physicists realized that Weber's bars, though visionary, lacked the sensitivity needed to detect spacetime's faint tremors. What was required was something far larger and more delicate, something that could measure distances with unprecedented precision. The concept emerged slowly, an enormous laser interferometer in which light would travel along two long arms, reflect from mirrors suspended in vacuum, and recombine to reveal any slight change in their lengths. A gravitational wave passing through Earth would stretch one arm and compress the other, altering the pattern of the light. This interferometer would not search for vibrations in solid metal. It would search for the stretching of space-time itself. Thus began the creation of LIGO, the Laser Interferometer Gravitational Wave Observatory. Building it required decades of work. Each observatory, one in Washington and one in Louisiana, contained two long arms set at right angles, each several kilometers in length. Vacuum chambers had to be kept extraordinarily clean. Mirrors had to be polished with atomic-level precision. Seismic isolation systems had to reduce ground motion to near silence. Even the tilt of Earth's crust as it cooled at night could interfere with measurements. Every vibration from the outside world had to be filtered away so that the tiniest whisper of a gravitational wave could be heard. By the early 21st century, LIGO had become one of the most sensitive scientific instruments ever built. It could detect changes in distance far smaller than anything previously measurable. Yet even this sensitivity was not enough. Engineers upgraded the observatories, enhancing their stability and increasing their ability to isolate noise. The upgrades transformed LIGO into a detector capable of listening to the universe at the edge of possibility. And then, on a quiet morning in 2015, Spacetime spoke. The signal that arrived was faint but unmistakable, a rising tone, increasing in frequency and energy before cutting off suddenly. This was the sound of two black holes spiraling inward, colliding and merging into a single heavier black hole. The waveform matched the predictions of general relativity with extraordinary precision. Every curve in the signal matched Einstein's equations. Every detail aligned with the physics of curved space-time. After a century of waiting, gravitational waves had been detected. This discovery did not belong to theory alone. It belonged to the universe. A ripple that had traveled more than 1 billion years had passed through Earth, stretching and compressing space by an amount smaller than a proton, and LIGO had heard it. Einstein's most elusive prediction had become an observable feature of nature. Yet this was only the beginning. More signals followed. Black hole mergers, neutron star collisions, and space-time events that had never been seen before. A new form of astronomy had been born, one that would reveal the universe not through light, but through the vibrations of space-time itself. The first detection of gravitational waves transformed the scientific landscape, but its true significance emerged only when the universe continued speaking. Once LIGO had become sensitive enough to hear those faint ripples, space-time revealed that it was far from silent. The second major detection arrived only months after the first, followed by more in rapid succession. Each signal was a fingerprint of a distant cosmic collision, shaped by masses and motions so extreme that no telescope observing light alone could fully describe them. With every detection, gravitational wave astronomy began to evolve from a singular triumph into a new way of observing the universe. The form of each signal carried hidden information. When two black holes spiraled toward each other, their orbits tightened as they radiated gravitational energy. This loss of energy caused the frequency of their motion to rise. The waveform grew sharper, climbing in pitch until the final moment when the two black holes collided and merged. The sudden cutoff that followed marked the birth of a new, more massive black hole, settling into equilibrium. What had once been pure mathematics now appeared as a measurable sound, a sweep of rising frequencies that revealed the last heartbeat of a system billions of years old. Each new detection strengthened the evidence for general relativity. The mass of the black holes, the rate at which their orbits shrank, and even the shape of the final merged black hole formed a consistent pattern that matched Einstein's predictions precisely. The universe behaved exactly as curved spacetime required. There were no unexpected deviations, no hidden forces, no extra signals that violated the theory. Even the speed of gravitational waves, measured by comparing detection times at different observatories, matched the speed of light within extraordinary limits. The harmony between theory and observation reached a level of precision rarely seen in physics. But the most dramatic revelation came in 2017, when LIGO and its European partner Virgo detected a new kind of signal. Unlike the short, powerful chirps of black hole mergers, this waveform lasted nearly a minute. It began at a low frequency and climbed slowly, tracing the careful spiral of two neutron stars orbiting one another. Neutron stars, the dense remnants of massive stars, contain matter so compressed that a teaspoonful would weigh billions of tons. Their collisions were expected to be among the most energetic events in the universe, producing both gravitational waves and electromagnetic radiation. This event, known as GW 170817, became the first cosmic collision observed through two completely different messengers. As LIGO and Virgo recorded the gravitational waves, space telescopes around the world detected a burst of gamma rays. Moments later, optical telescopes saw the fading glow of the explosion, followed by radio and infrared signals that revealed the debris expanding outward. The universe had spoken in multiple languages at once, the tremble of space-time and the flash of light. For the first time, astronomers could watch a cosmic catastrophe unfold through complementary channels, each revealing a different layer of reality. This multi-messenger event confirmed long-suspected theories about the origin of heavy elements. The observations showed that neutron star collisions forged gold, platinum, and other rare materials, scattering them into space. It revealed that some of the elements found on Earth were born in these distant explosions, carried across the galaxy long before the solar system formed. General Relativity had not only predicted the behavior of space-time, it had guided astronomy toward understanding how the building blocks of planets and life itself were created. As gravitational wave detections multiplied, scientists realized that they were seeing a population of objects that had once been invisible. Stellar mass black holes, some far heavier than expected, appeared regularly in the data. Neutron stars merged with companions of various sizes. Mixed systems, where black holes devoured neutron stars, added yet more variety. Each event became a laboratory in which the universe tested the limits of Einstein's equations. Despite these increasingly extreme tests, general relativity remained unbroken. Its predictions for the polarization of gravitational waves matched every observation. The wave's phase and amplitude followed the theory's equations perfectly. The shapes of the signals agreed with the mathematics describing curved space-time. Even the most violent events in the cosmos, places where gravity reached its greatest strengths, behaved exactly as Einstein had foreseen. Gravitational wave astronomy opened a door into realms that had been locked to optical telescopes for all of human history. It allowed astronomers to observe dark systems that emitted no light at all, to study collisions that unfolded in the deep vacuum of space, and to understand gravity not just as a static influence, but as a dynamic, vibrating force woven into the fabric of reality. Yet even as gravitational waves revealed their secrets, a deeper truth waited quietly beneath them. Newton's gravity still lived inside Einstein's equations, not erased but absorbed, appearing naturally wherever gravitational fields were weak and speeds were slow. Understanding this relationship would become essential for seeing how two theories, separated by centuries, fit together in a single cosmic story. The steady rhythm of gravitational wave detections soon revealed something profound. The universe was filled with collisions, spirals, and mergers that had occurred unseen for billions of years. Before the age of interferometers, these events left no trace in humanity's instruments. Telescopes measured light, detectors measured particles, but the most violent gravitational interactions emitted neither light nor particles in quantities large enough to reach Earth. They whispered only through spacetime itself. Now, for the first time, those whispers had become audible. Each new detection brought with it a deeper understanding of how gravity behaves under extraordinary conditions. The signals painted pictures of black holes circling each other at half the speed of light, sending out ripples that carried away enormous amounts of energy. With each orbit, they spiraled closer, tracing a cosmic dance that had been unfolding long before life existed on Earth. When they finally merged, the energy released in gravitational waves exceeded the output of all the stars in the observable universe. Yet it arrived on Earth as an almost imperceptible trembling of distance. What made these detections remarkable was not just their violence, but their clarity. Each waveform matched with precise fidelity the mathematical templates generated from Einstein's field equations. This agreement reached into every detail: the rate at which the frequencies rose, the moment the merger occurred, the ring-down phase where the final black hole settled into equilibrium. Even the pattern of stretching and squeezing matched the polarization predicted by General Relativity. No alternative explanation survived. The waves were unmistakably those produced by curved spacetime behaving exactly as Einstein had described a century earlier. In some detections, physicists found subtle differences in mass and spin, hinting at the diversity of black hole populations. Others revealed systems that challenged earlier assumptions, such as black holes too heavy to have formed through ordinary stellar evolution. These discoveries forced astronomers to explore new models of star formation, stellar collapse, and the environments where massive binaries might develop. Gravitational waves had become not just a tool for testing relativity, but a new branch of observational astronomy, reshaping the understanding of how stars lived and died. The most dramatic findings emerged when gravitational wave observatories collaborated with telescopes across the electromagnetic spectrum. The multi-messenger event of 2017 remained the most striking example. Gravitational waves told astronomers when and how the collision occurred. Gamma rays revealed the blast's immediate energy. Optical telescopes traced the radioactive glow of freshly formed heavy elements. Radio observatories followed the expanding debris as it interacted with surrounding gas. Each wavelength added a piece to the puzzle, forming a complete story that no single instrument could tell alone. These observations confirmed the large-scale predictions of general relativity with extraordinary depth, but they also reaffirmed an elegant truth. The equations that describe the curvature of space-time were universal. They applied with equal authority to black hole mergers billions of light years away and to the delicate timing of atomic clocks on Earth. They governed the paths of starlight during an eclipse and the rhythm of a neutron star's final spiral. Gravity, in Einstein's vision, unified the cosmos through a single geometric principle. Yet even with these triumphs, general relativity did not erase the legacy of Newton. It contained it. In the weak gravitational fields found around planets, moons, and spacecraft, Einstein's equations reduced perfectly to the familiar Newtonian form. Engineers designing orbits still used Newton's gravitational constant. Navigators still used Newton's laws for everyday calculations. Only in situations where space-time curvature became significant, near the Sun, in precise satellite timing, or in extreme astrophysical events, did relativity reveal its deeper, richer structure. Thus, the story of gravitational waves marked not the end of Newtonian gravity, but the completion of its transformation. Newton had described gravity as a force. Einstein revealed it as geometry. Gravitational waves were the final confirmation that space-time was not rigid but dynamic, capable of vibrating, stretching, and carrying energy across the cosmos. With the universe now speaking through both light and gravitational waves, and with every major prediction of general relativity confirmed, the time had come to understand how Newton's vision remained embedded within Einstein's. The next chapter would show how the old theory survived inside the new, preserved in the gentle corners of the cosmos, where velocities were slow and gravity mild. For more than 2 centuries, Newton's vision of gravity guided humanity with an elegance that seemed beyond question. His description of a force acting between masses explained the falling of objects, the motion of planets, and the dance of comets weaving through the solar system. It revealed Neptune, guided the tides, and illuminated the rhythm of celestial mechanics. Yet when Einstein reshaped gravity into a manifestation of curved spacetime, Newton's law did not crumble. Instead, it found its true place. Einstein's equations did not erase Newton. They embraced him, revealing that the classical view of gravity was the shadow of a deeper geometric truth. In the quiet regions of the universe where gravity is gentle and velocities remain slow, space-time is nearly flat. Einstein's field equations reduce themselves to simple forms, and these forms yield Newton's familiar inverse square attraction. Planets move along paths that match Newton's predictions. Satellites follow trajectories that engineers can reliably compute using classical mechanics. Bridges stand firm. Orbits remain stable. In these calm environments, relativity hides beneath the surface, whispering corrections so small that they vanish into the background of ordinary experience. Newton's gravity thrives here not because it is exact, but because Einstein's universe permits it as an approximation of extraordinary accuracy. This relationship becomes clear in the mathematics. When the curvature of space-time is small and velocities remain a tiny fraction of the speed of light, Einstein's equations gently flatten into Newton's law. The geometry stretches only slightly. Time flows almost uniformly. Light barely bends. In this delicate balance, Newton's force law emerges naturally. It is the lowest note in the harmonic structure of space-time, the simple melody that becomes audible when the deeper symphony grows quiet. Yet the harmony shifts when gravity strengthens. Near the Sun, where space-time curves more sharply, Newtonian gravity begins to falter. The orbit of Mercury reveals this boundary with exquisite clarity. Newton's equations predict most of Mercury's motion, yet they cannot account for the extra 43 arcseconds of perihelion shift each century. Einstein's geometry explains this drift effortlessly. The curved spacetime around the Sun tilts Mercury's orbit slightly forward with each revolution. General relativity fills the gap, not through correction, but through the natural structure of spacetime itself. Binary pulsars expose the same truth on a far grander scale. These dense remnants of massive stars orbit each other with speeds and gravitational fields that dwarf anything in the solar system. Their pulses arrive on Earth with astonishing regularity. When scientists track these pulses over years, they discover that the system's orbit slowly decays. Energy leaks away as gravitational radiation, a phenomenon Newton's theory cannot predict. Einstein's equations describe the decay precisely. The shrinking orbit becomes a testament to spacetime's ability to ripple. The pulsars trace curves in a geometry that Newton's world could not imagine. Meanwhile, on Earth, clocks reveal the difference between classical and relativistic gravity with quiet precision. A clock raised a meter above the ground ticks faster than a clock left on the floor. Newton's theory has no language for such a change. General relativity predicts it exactly. Satellites in orbit carry clocks that run faster because they reside in a region of weaker gravity. Engineers must correct for this relativistic drift to maintain the accuracy of navigation systems. Without Einstein's adjustments, the positions calculated by these systems would drift by kilometers each day. In all these environments, Newton's gravity remains useful, not because it is fundamental, but because it is contained within Einstein's theory. Relativity governs everything, yet it allows Newton to describe the world where space-time barely curves. It allows spacecraft engineers to compute trajectories quickly. It allows architects and navigators to rely on classical equations. Newton was not wrong, he was incomplete. Einstein revealed the deeper page on which Newton had been writing. As technology advanced, modern experiments pressed relativity harder than ever. Observations of gravitational lensing across galaxies, timing variations in distant pulsars, and the behavior of matter near black holes all demanded the full machinery of curved space-time. Newton could not follow the universe into these extreme realms. Yet his theory remained intact within its natural boundaries, preserved and honored by the equations that expanded upon it. Thus, the relationship between Newton and Einstein became a model for scientific progress itself. A successful theory is not discarded when a deeper one arises. It is understood more fully. Newton's world survives within Einstein's, just as Einstein's may one day survive within a future theory yet to be discovered. But before humanity reaches beyond relativity, it must first examine how modern experiments have tested Einstein's ideas with unprecedented precision, pushing them to their limits and confirming them again and again. The 20th century revealed the beauty of general relativity. The 21st century tested it with an intensity that no physical theory had endured before. What began as a daring geometric vision became one of the most precisely confirmed frameworks in all of science. From orbiting gyroscopes to deep space signals, from star clusters to cosmic background radiation, the universe offered its secrets, one measurement at a time. And each time, Einstein's equations stood firm. One of the clearest modern tests came from Gravity Probe B, a spacecraft designed to detect the curvature and twisting of space-time around Earth. Within this satellite were 4 nearly perfect spheres, among the smoothest objects ever made by human hands. As the satellite orbited Earth, the spin axes of these gyroscopes drifted by tiny amounts predicted by general relativity. The geodetic effect revealed how Earth's mass curved spacetime. The frame dragging effect revealed how Earth's rotation twisted it. These drifts were so small that it took years of analysis to extract them from the data. When the results were finally published, they matched Einstein's predictions closely. The shape of space-time near Earth conformed to the geometry written in 1915. Meanwhile, the cosmos provided even more dramatic tests. Binary pulsars, spinning with incredible precision, acted as cosmic clocks measuring gravity under extreme conditions. Their orbits decayed as they emitted gravitational radiation, a process that Newtonian physics could not describe. The rate of decay matched Einstein's predictions almost perfectly. Each pulsar system became a laboratory showing that general relativity governed the motion of dense stars with unwavering consistency. At the center of the Milky Way, stars orbited Sagittarius, a star with velocities so high that Newton's gravity could not account for them. When the star S2 swung close to this supermassive black hole, its light shifted toward the red in a direct observation of gravitational time dilation. The orbit matched Einstein's equations exactly. Space-time bent the path of starlight and slowed the flow of time just as the theory required. At even larger scales, galaxies and galaxy clusters bent light into arcs and rings through gravitational lensing. Telescopes captured these distortions and mapped them with increasing precision. The patterns reflected the curvature of space-time on scales stretching across millions of light years. Once again, general relativity predicted the observations faithfully. Even the faint distortions in the shapes of distant galaxies, known as weak lensing, aligned with the theory. Closer to home, spacecraft signals passing near the Sun slowed slightly as they moved through curved space-time. This Shapiro time delay, measured with exceptional accuracy by the Cassini mission, matched Einstein's predictions to high precision. Laser reflectors left on the Moon by the Apollo missions allowed scientists to measure the Moon's orbit to millimeter accuracy. The results confirmed the predictions of general relativity about how Earth and the Moon move through curved space-time. Laboratory experiments grew even more sensitive. Atomic clocks detected time dilation over height differences smaller than a step. Atom interferometers revealed the curvature of space-time through the shifting wave patterns of falling atoms. Variations in Earth's gravitational field, mapped by satellite missions, matched the relativistic corrections applied to their orbits. Everywhere scientists looked, the theory held firm. Yet the greatest confirmation came from the most violent events in the universe. Gravitational waves, detected by LIGO and Virgo, carried information about black hole mergers, neutron-star collisions, and cosmic upheavals billions of light years away. Their waveforms matched general relativity so precisely that even the smallest details aligned. The speed of these waves matched the speed of light. Their polarization followed Einstein's predictions. Their energy loss matched the equations of curved space-time. General relativity survived every test, not because it was perfect, but because the universe itself obeyed its geometric rules. And yet, for all its triumphs, the theory remained incomplete. It offered no explanation for dark matter or dark energy. It did not merge with quantum mechanics. The cosmos hinted at a deeper truth, but it revealed no deviation in the curvature of space-time. Thus, Einstein's theory became both a triumph and a doorway. It described gravity with unmatched accuracy, yet it pointed toward mysteries still unsolved. General Relativity replaced Newton not by destroying him, but by absorbing him. And the next great theory, whatever form it takes, will almost certainly absorb Einstein in the same quiet, elegant way. In the faint stillness between distant galaxies, where starlight travels for ages without bending and time drifts in near-perfect calm, the universe holds its final secrets just beyond the reach of every instrument built so far. General Relativity has traced the great curves of space-time, and quantum theory has followed the restless tremors hidden inside matter, yet neither has stepped into the other's territory. It is as though two truths run silently side by side, waiting for a moment when the cosmos allows them to meet. Perhaps that meeting lies in the heart of a collapsing star, where gravity squeezes matter past the limits of known physics, or in a realm where particles move with energies no collider has ever reached, or in some deeper fold of space-time, where geometry twists in ways no equation has yet described. No observation has revealed this hidden place, yet every test of Einstein's theory hints that something still waits in the silence. The universe has shown only enough to make us certain that we do not yet see the full picture. And so the last question lingers with a quiet, haunting weight. If every law we know is only a glimpse of a wider pattern, what unseen structure shapes the world from beneath the surface, guiding the cosmos with a rhythm we have not yet learned to hear?